Welcome everyone in lecture number 33. In this video lecture, I will discuss some applications of finite Fourier sine and cosine transforms to solve boundary value problems. So we have already discussed about finite Fourier sine and cosine transforms and the conditions in which we can apply these transforms to the given function. So today we solve directly some problems which are the boundary value problems. But the question is, how do we know that we should apply sine transform on the given problem or cosine transform? So the answer is that on the uh, basis of the given condition in the given question, we choose sine or cosine transform. So I'll show you first of all the condition in which we should apply the sine transform and cosine transform. So we first of all find Fourier sine transform of second derivative of u with respect to x. This is finite Fourier sine transform. Okay. So if we apply finite Fourier sine transform on this differential equation, then we have 0 to L del 2u over del x square sine p pi x over L dx. By the definition of finite Fourier sine transform, this is the function fx. Okay. So we integrate this by parts. First function, this is our first function, and this is taken as second function. So first function into integration of second function. So we write first of all del u by del x, and then we write sine p pi x over L. Then we apply limit in this part minus integration 0 to L del u by del x cos p pi x over L, differentiation of this, and the extra part which is in denominator, which is p pi upon L, it will become not in the denominator, it will in the multiplication. So we have p pi over L because we are differentiating this function. So we assume that del u by del x we don't know the value of del u by del x at the upper limit. So we write this as it is. But when you substitute L here, you will get sine p pi, which is 0. And at lower limit, this is automatically 0. So this whole term vanish. ये पूरा term 0 हो जाएगा. What is left is this term. So we have minus p pi over L u x comma t cos p pi x over L 0 to L minus integration of u x t, because the derivative of cos is negative, so we have positive sign here, sine p pi. Let me write this expression in the next line because it is not coming in this line. So let me write it again. P pi over L ux comma t cos p pi x over L minus 0 to L ux comma t sine p pi x over L into p pi over L. So we have minus p pi over L u L comma t, and cos p pi is minus 1 raised to the power p u L comma t, and at lower limit this will be 1 and we are left with u 0 comma t. Okay, and here we have p minus this p pi over L will get multiplied with this p square pi square over L square, and this integral, if you see it carefully, this is Fourier sine, finite Fourier sine transform of the function u, which can be denoted as us bar. Okay, so you see here that we need the value of u at 0 comma t and L comma t. These two are needed to solve this. Okay, so this is what happened when we apply Fourier sine transform to the second derivative equation. Let's see what happened when we apply Fourier cosine transform in the same differential equation. This is 0 to L del to u over del x square cos p pi x over L dx. Again we use integration by parts, del u by del x cos p pi x over L 0 to L minus del u by del x sine p pi x over L into p pi over L dx. This is you can denote this by ux L comma t at when we substitute L at in place of x, and cos of p pi is minus 1 raised to the power p. At lower limit this will be ux at 0 comma t, and this is mm, minus plus p pi over L integral 0 to L del u by del x sine p pi x over L dx. ux L comma t, इसका मतलब del u by del x की वैल्यू at L comma t. Okay, this is not mu, this is u. This is u. Minus 1 raised to the power p minus ux 0 comma t plus p pi over L ux comma t integration of this, and this function is as it is 0 to L minus integral ux comma t. Differentiation of sine p pi x is cos p pi x over L into p pi over L dx. ux L comma t minus 1 raised to the power p minus ux 0 comma t. This is the value, this whole expression will be 0 because at upper limit sine p pi will be 0 and at lower limit this is a 0. So this term vanish and this p pi will get multiplied with this p pi so that we have p square pi square over L square. And this integration is nothing but Fourier, finite Fourier cosine transform of the function u, that is denoted by UC bar. So you see that we need the derivative value at 0 comma t and L comma t. So this is the hint that you have to apply whether sine transform or cosine transform. If you are given the derivative value at 0 and L, you apply Fourier cosine transform. If you are given the value of u at 0 and L, you will apply Fourier sine transform. So let's see one example. Solve del u by del t is equal to del 2u over del x square, where x lies between 0 and 4, t is greater than 0, such that u0 comma t is 0 and u4 comma t is 0 and ux comma 0 is 2x. So as you can see here that limit of the variable is from 0 to 4, which is finite. So we will apply here finite Fourier sine or cosine transform. Now since the value of u is given at 0 and 4, which is required, as you can see here, 0 value of u at 0 and L, which is required when we apply Fourier sine transform. So these two values are given to us. That means we will apply here Fourier, finite Fourier sine transform. Okay. So we are given this equation. Del u by del t is equal to del 2u over del x square. So we apply here finite Fourier sine transform. We get 0 to 4 del u by del t sine p pi x over 4, 0 to 4 del 2u over del x square sine p pi x over 4 dx. Now since this derivative integration is with respect to x and this derivative is with respect to t, so this can be written as d over dt of 0 to 4 ux comma t sine p pi x over 4 dx. And here we apply integration by parts rule, del u by del x. We take this as first function and this as second function. first function into integration of second function minus integral del u by del x cos p pi x over 4. P pi over 4 will come outside dx. Zero to 4. So this can be written as dus bar over dt minus, this will be 0 at both limits, and this will be uh, uh, plus p pi over 4 ux comma t cos p pi x over 4 and limit 0 to 4 minus p pi over 4 integral 0 to 4 ux comma t sine p pi x over 4, because the derivative of cos is negative, so we have positive sign here. This is equal to sine. I'm sorry. We have negative sign here. And this is like this. Okay. So we need the value of u4 comma t, which is 0, and at lower limit this will be u0 comma t, which is also 0, so this whole term vanish, and we are left with dus bar over dt is equal to minus p square pi square over 4 and this expression is nothing but us bar. Okay, so this is also 4 square. Now we are given we can separate the variables. Dus bar over us bar is equal to minus p square pi square over 16 dt, so that we have log of us bar is equal to minus p square pi square over 16 t plus log of c. This implies us bar is equal to c e to the power minus p square pi square over 16 into t. okay, where C is constant. So this is nothing but U S at P comma T. This is C E minus P square pi square over 16. When we put T is equal to 0, we have U S bar P comma 0. Because we have T here, so we can put T is equal to 0. We cannot put P is equal to 0. P cannot be 0 because we have two variables here, X and T. So we can put T is equal to 0 so that we have C. So we need the value of this. So for this, you are given this condition ux comma 0 is equal to 2x. So ux comma 0 is equal to 2x, so that we take the finite Fourier sine transform of this. And we have 0 to 4 2x sine p pi x over 4 dx. This is denoted by us bar x p comma 0, because after solving it you will get the function of p, so we'll replace x by p, and it is equal to, we solve this first function integration of second function minus derivative into integration again sine p pi x over 4 over p square pi square over 16. Apply the limit. So we have 8x over p pi cos p pi x over 4 plus 32 over p square pi square sine p pi x over 4. Now we apply the limits. So we have minus 32 over p pi into minus 1 raised to the power p, and because cos of p pi is minus 1 raised to the power p, the sine p pi is 0, and up at lower limit both will be 0. So we have this 32 over p pi into minus 1 raised to the power p plus 1. So we substitute this value in this equation. So from 1, C will be 32 over p pi minus 1 raised to the power p plus 1. ये C की वैल्यू आ गई. अब हम C की वैल्यू यहाँ सब्स्टिट्यूट करेंगे in star, substituting the value of C in a star, we get US P comma T 32 upon P pi minus 1 raised to the power P plus 1 e raised to the power minus P square pi square over 16. This is Fs of Ux comma T. Okay. So next step is to take inverse finite Fourier sine transform of this expression. Ux comma t is f as inverse of this whole. Okay. So ux comma t is by definition, it is 2 upon L, which is 4, summation usp comma t sine p pi x over 4. So we have 1 upon 2 of 32 upon p pi. So we can take 32 upon pi outside. So that we have 16 upon pi. Summation minus 1 raised to the power p plus 1 over p. E raised to the power minus p square pi square. This is t also. I have skipped this. Yes, we have t here also. T over 16 into sine p pi x over 4. This is the answer, where summation is over p, and the summation varies from I think 1 to infinity. Okay. So we leave it here. This is the answer. Next, move on the second example. Second example is solve del u by del t k del 2u over del x square such that del u by del x is 0 when x is equal to 0 and x is equal to pi. दोनों पर ही ये 0 है. T is greater than 0 in both cases. And u is a function of x at t is equal to 0. This is initial condition. X varies from 0 to pi. These are the boundary conditions. This is the boundary condition. And this is the initial condition. Initial condition वो होती है जो टाइम t is equal to 0 पर given होती है. और बाउंड्री कंडीशन जो बाउंड्रीज पर x की जो बाउंड्रीज हैं उन पर फंक्शन की वैल्यू क्या है उस पर जो वैल्यू गिवन होती है दैट इज बाउंड्री कंडीशन. तो क्योंकि ऑब्वियसली यू आर गिवन द डेरिवेटिव वैल्यू एट द बाउंड्रीज, सो वी अप्लाई फोरियर कोसाइन ट्रांसफॉर्म्स. Fourier, finite Fourier cosine transform on the given equation. So limit is from 0 to pi del u by del t cos px, because L is pi, dx 0 to pi k del 2u over del x square cos px dx. So we write this as du c bar over dt. and here we apply integration by parts rule. We always take this as first function and this as second function. We have here p, and because the derivative of cos is negative, so we have positive sign here. Sine px dx. The derivative value at pi is 0, and at x is equal to 0, this is again 0. So this whole term is 0. So we are left with k into p. We will give the reason here why this term is 0. Okay, I'm not mentioning here. Kp, again we integrate this by parts. Ux comma t sine of px 0 comma pi minus integral ux comma t cos px dx. Okay, so we again this whole will be 0 at upper limit as well as at lower limit, because sine p pi is 0 as well as sine 0 is 0. So this will be 0. You should write the reason why they are 0. Okay, so we multiply this kp with this p, so that we have duc bar over dt is equal to minus kp square, and this is nothing but for finite Fourier cosine transform of the function u, which is denoted by uc bar. So we do the variable separation and then integration, so that we have the value of uc bar is equal to c raised to power minus kp square t. Putting t is equal to 0, we have uc 0 comma t, sorry, p comma 0 is equal to c. So we need this value. We use the we write this as an usual form, which is 0 to pi u x comma 0 dx cos px. Either you can take this इस कंडीशन का आप फाइनाइट फोरियर कोसाइन ट्रांसफॉर्म ले लीजिए, या इस कंडीशन को आप इसकी डेफिनेशन में कन्वर्ट कर दीजिए, बिकॉज दिस इज अ फाइनाइट फोरियर कोसाइन ट्रांसफॉर्म ऑफ द फंक्शन u x comma 0, जिसकी शॉर्ट जिसका नोटेशन ये है, तो हम इसको इसके ओरिजिनल फॉर्म में लिख रहे हैं. एंड u x comma 0 आपको क्वेश्चन में गिवन है कि ux, 0 at t is equal to 0 का मतलब ux, 0 की वैल्यू fx है, तो यहाँ पर हम fx लिख सकते हैं. तो ये c की वैल्यू है, तो ये वैल्यू आप c की इक्वेशन नंबर यहाँ पर इसको हम 2 कह देते हैं. इक्वेशन नंबर 2 में वैल्यू सब्स्टिट्यूट करें, so that we have uc bar is equal to e raised to power minus kp square t integral 0 to pi fx cos px dx. Now the next step is, because UC bar is nothing but Fourier cosine transform of ux comma t. Okay. Let me write the whole expression. Fx cos px dx. So ux comma t is Fourier cosine inverse of this expression, which is equal to 1 upon pi uc bar at 0 comma t plus 2 upon pi. This is by definition I am writing. You should look at the definition again if you don't remember the formula. uc p comma t cos px, where uc at 0 comma t is 0 to pi u x comma 0 mm, mm, okay, by definition. So this is given to you as fx dx. So you can replace this in this expression by this expression, and this UCP comma T is replaced by this expression. Okay. So finally we have ux comma t is equal to 1 upon pi integral 0 to pi fx dx plus 2 upon pi summation e raised to power minus kp squared t cos px. अब क्योंकि यहाँ पर p फंक्शन ऑफ x cos px है, तो यहाँ पर इसको हम y से रिप्लेस कर देते हैं, because that makes the confusion why cos px is written outside the integral. So we replace x by y. Okay. This integration is nothing to do with this cos px. Okay. You can also replace this variable x by y. You can write here fy dy. Okay, to make it different from x. So this is the answer. So I hope you understand this lecture about applications of finite Fourier sine and cosine transforms to solve boundary value problems. I have discussed 2 problems. I'll discuss some more problems in my next lecture. So if you like my lecture, you can press the like button and share it. And you can also subscribe my channel to get the notification of the next new video on this channel. Thank you again for watching the video.